Alright, I want to take a look at the mean value theorem and how it relates for integrals. And it's a pretty powerful theorem. And hopefully I'll do a good job explaining it. So I'm going to draw a graph here. And here's my A, here's my B, and here's my graph. And this right here is f of x. And so if I want to know the area underneath that curve, I would integrate from a to b f of x dx and use a fundamental theorem of calculus part 1. That would give me the antiderivative with b substituted in it minus the antiderivative of f with a substituted into it, and that would give me that area. Well, there's a rectangle somewhere, and I'm going to see if I can change colors. And I'm going to go to red. There's going to be a rectangle somewhere. That has an equivalent area. And the length of this right here is b minus a. And this right here would be the height. Okay, well that height is the same as right here if I could draw halfway decent. So I'm going to call that a c. So this height is going to be f of c. So the area of this rectangle which is b minus a, is my width or my base. Here's my height, f of c, is equal to this process of the antiderivative. Which means that I can say f of c is equal to f of b minus f of a over b minus a. Now, you've seen this before. This is, and I'll abbreviate, the mean value theorem. Here's this is the slope of a secant line. This is the slope of a tangent line. If we recall, lowercase f is the derivative of capital F, or capital F is the antiderivative of lowercase f. We also call this, and since I'm on this is the average rate, and this is instantaneous rate. Okay, and so what I can do, this allows me to figure out the average of all these values right here. And I'll show you what I mean by that. Let's say that over here I have a function f, and it is minus 2x cubed plus x plus 1. And this gives me, if I were to graph this, this gives me the rate of change. So this is a rate. That's what that function represents. So if I were to integrate that from -1 to 0, I would do this in this fashion, and it would give me -1/2 x to the 4th plus 1/2 x squared plus x evaluated from -1 to 0. And if I put 0 in there, and then if I put a -1 in there, I'd have a -1/2 plus 1/2 minus 1. And I'd get 0 minus a -1. I'd get an area of 1. So if this is a rate of change, like let's say it is feet per second, and these are seconds, this would give me my net area, okay, my net distance. I have a net distance of 1. Well, if I take that 1 and divide it by 0 minus a -1, this is a terrible example. I'd get 1 divided by 1, so my average rate in this case would be 1. All right, let me give you another example here. Let me clear. Again, my average rate in terms of integrals is going to be the same as 1 over b minus a from a to b of f of x dx. Sometimes you see it as this, a to b of f of x dx over b minus a. Or you can also see it like this, f of b minus f of a, b minus a. So if I have this graph, and over here this represents feet per second, and down here this represents seconds, and I get a graph that looks like this. Alright, and I have area in here. I wonder if I can get area in here. Yeah, perfect. So I have this purple area, and this purple area, since this is feet per second, these are seconds. If this is 0 seconds right here, and this is 15 seconds right here, and this is f of x, if I integrate this from 0 to 15 of f of x dx, this is going to give me, since this is entirely positive, since it's entirely above the x-axis, this is going to give me my total distance. The total distance perhaps that I walked in 15 seconds. But if I divide it by 15 minus 0, this is my b, this is my a, and I divide this by 15, I'm taking my total distance and dividing it by 15. That's going to give me my average rate. Now think about this. I have an infinite number of rates that follow this line, right? My y values are rates, and so they're changing as I move along 15 seconds. I've actually averaged an infinite number of rates that I had during this walk. And so this is going to give me my average rate of change. Let me give you another example. And I did this in class. And let's say I have two tables. And this stands for time, and my time will be in minutes. Let's change it up a little bit. And over here, here's my distance, and my distance will be in feet. Okay. And I think this is kind of the example I used in class here. Let's say at time 0, I haven't walked anywhere at all. But at 5 seconds, I've walked 9 feet. And at 9 seconds, I've walked 15 feet. Okay, so if I wanted to figure out my average rate, I know that in 9 seconds I've walked a total of 15 feet. So one way to look at it is I started at the point 0, 0, and then I'm at the 9:15, and I would take my slope of 2 points. Remember, this is feet, this is seconds. I'm going to get 15 over 9, and that's going to give me 5 over 3. So I have 5 over 3 feet, I think I said seconds, feet per minute. Alright, that's your typical problem. I want a distance of 15 feet in 9 minutes. Now let's use the same table and have the same values here, but I'm going to find them differently. So again, this is my time in minutes, but rather this is a rate. It's my speed that I'm walking 15 feet per minute. So at 0, 0, I'm not walking at all. At 5 minutes, I'm walking 9 feet per minute, and at 9 minutes, I'm walking 15 feet per minute. So if I did this, and did this 15 minus 0 and this 9 minus 0, what this is feet, this is minutes down here. This is feet per minute here. So I'd have 15 feet per minute divided by 9 minutes. That gives me feet. This gives me 5/3 feet per minute squared. That gives me my average acceleration. That's not what I'm looking for. I'm looking for my average rate of change. What's my average rate that I was walking? Well, what I can do here is I can use the idea of Riemann sums. And I'll use a right Riemann sums. I think it's a little bit easier. So here I have 5 minutes. Right here I have 9 minutes. And these are minutes. And up here I have my rate. I have 9, and then I have 15, and these are feet per minute. And right here I have 5, 9, and I have 9, 15. I can create two rectangles and say this is an approximate distance of 45 feet, and this is approximate distance of 60 feet, right? 4 by 15, 5 by 9, and so I have 105 feet approximately. That's approximate integral of 0 to 9 of f of x dx. It's approximate because I'm using the rectangles. Well, if I divide that by 9 minus 0, or divide it by 9, this is 9 minutes that I'm dividing. So I'm going to get feet per minute. So my average rate of walking is approximately, say, 35, I think is 105 divided by 3. 35 over 3 feet per minute. Right? And that's what we're doing when we are looking at this. Now let me go to the notes. Let me add an image here, and I got a place called Notes. I took a screenshot of the notes. I think it's this one right here. And this is in the book. Find the average value. Well, when I'm looking for average value, what I'm doing is I'm really looking for average rate. And what you're going to do here is you're going to integrate my average value of f of x. What's my average of all these values here? So I'm going to integrate from 1 to 4 of 3x squared minus 2x dx. And I'm going to multiply that by 1 over 4 minus 1, which is my b over a. So this is going to be 1/3 times the integration from 1 to 4 of 3x squared minus 2x dx. Okay, so what does that look like? I have to first figure out the antiderivative, which is x cubed minus x squared evaluated from 1 to 4, and I'm going to take 1/3 of this, which means I'm going to take 1/3 of my parentheses is going to be 4 cubed minus 4 squared minus, now I got to plug my 1 in there, 1 cubed minus 1 squared, and this is going to be 1/3 because I'm figuring out average again. This is going to be 64 minus 16. This is going to be 0, and I get 64 minus 16 is 48 times 1/3, and I'm going to get 16 as my answer. That's my average value. In other words, all my y values from 1 to 4, the average of all my y values is 16.